you're not applying any force to accelerate it anymore.
Is that true? You're not applying a force to accelerate anymore. If I'm holding it, is it accelerating?
Yeah.
It is. Because of what force? Tension. Still tension acting on it. So there is a force. Right? So I'm going to disagree with the latter part of the statement, that there is no force. Even when you don't talk like this anymore, you're holding it, there's still a force acting on it. But it still doesn't slow down. Why not? You want to maybe clarify the statement or take it a step further? Yeah, tell me your name.
Alex.
Alex.
The force is perpendicular to the actual direction of motion. And since we have the work equals FD cos theta, the tension is not actually doing any work onto the ball that's swinging around. So there's not actually any change once we let go, or change in once the tension is not actually changing the velocity.
Right, okay. So the point is that there's a force on this thing because it's accelerating. So each point there's a force pointing inwards toward your hand. So there is a force, but the point is that the work done is zero because when you dot it with the displacement, these are vectors. If I draw this face down, you have tension pointing in and you have it's going in like that. The dot product of these two vectors at all times in the circle is zero, so it does not work. What is this force called that does not work? What kind of force is it? It changes direction but it doesn't do any work.
Constraining force?
Constraint force, yeah, it's a constraint force. So it constrains the path, the particle in movements of direction, but the speed stays the same. So the answer was C because there's no work done. And we know that the change in kinetic energy, once a change in potential energy, so I'm going to say the change in kinetic energy equals the work done on it. There's no potential out there, so that equals the work done. This is zero, so you can't change kinetic energy, so the velocity stays the same. Right, so it is possible to have forces acting on an item without them actually changing speed. Right, the forces may do no work. But for that to happen, the force and the displacement of the particle at that instant have to be in perpendicular directions. There's one more force that is also usually a constraint force, which is the normal force. If I'm pushing something on the ground, I'm pushing it in a certain direction, but the normal force always points perpendicular to my push. So that won't do any work either. So the normal force itself will not slow any objects down. Any questions on that? Quick conceptual questions to clarify that statement. So in that case, let me do a couple of problems that involve finding missing quantities in problems of energy. Let me start with the one from the homework. This problem, I didn't think it was that tricky because it was only one or two steps, but it seems to be giving a lot of people problems. So let me go over it. It's number 8. Yeah, number 8 here. It says that a block of mass 12 kilograms is sliding down from rest along an inclined plane that's frictionless. And it's stopped by a strong spring that basically when it comes down the ramp, it compresses the spring until it stops. And at that moment, it's asking you, right when it stops, what is the how much does the spring actually compress? The situation would look like this. Initially, it would look like that. The spring here is going to go down. And then, after it has gone down, this thing will be resting against the spring. Let me draw this a little bigger first. So the spring is first uncompressed. There's no potential energy there. And then you get it compressed. And the block is resting on it. And the problem, let me read this carefully. It says that the block slides down a total distance of 3 meters from the point of release to where it comes to rest. Which means that, if I draw where it was originally, this distance, where it was, I guess let's say right in the middle of it, to where it comes to rest is 3 meters. Okay. Now, to solve these types of problems, you always want to start with the statement that energy is conserved unless you take out energy from the system or put it back in. So if you haven't been in the discussion section where I'm writing this formula down, this is not something that Professor R uses, nor is it the one in the book, but it's very close. This is the one I use because, and again, this T, by the way, is kinetic energy. And this is potential energy. And I've derived this a couple of times in class, so I'm not going to go through the derivation right now. The point is that this potential energy term comes from this term that used to be on the right-hand side of the equation, which I moved over. And this is when it's a conservative force. I can just write it as the I can write the conservative force as an as a derivative of something else, and that something else is called potential function. And the point is that if I can write it like that, I don't have to do the integral. All that matters is the potential at the beginning and the end. And that term comes over here. So this actually is some sort of force, but this deals with only conservative forces. And those examples that we've seen in our class have been gravity and springs. And another one that Professor Michelson discussed in class today was electricity, which is going to come up a lot of times in 1D or 2D for you guys. So this is going to be conservative forces. And just to recap, a couple attributes of conservative forces. First of all, the work that they do is path independent. Doesn't matter how you got from point A to point B. The work will be the same. Second of all, they can be written as an antiderivative. That's something Professor Michael didn't say in class, but that's something that's really crucial with that. The fact that you can write them as an antiderivative of a different function, as a derivative of a different function. And then lastly, the amount of work you do on a closed path is zero. So if you push something and it's got a conservative force, not push, but let's say it goes to a conservative force and ends up back where it started, the total amount of work done has to be zero. And he mentioned in class that he had kind of a nice situation where if it wasn't zero, you could just get back more work than you put in, and you could have an infinite source of energy. So these are conservative forces, and these will typically include gravity and springs. And let me put electrical energy because that'll come up as well later on. Another one is actually magnetic energy, but we'll talk about that later. And then on the right-hand side, so the left-hand side is total mechanical energy. Kinetic plus potential is total mechanical energy. That's what the book calls it. And so what the point is that this total mechanical energy is always the same all the time, unless you put in some work into the system or take it out. So these are what you're doing to the system externally. You may be taking away its heat. You may be taking away its sound or something. You may be physically pushing it or slowing it down. All these types of work are going to change your total mechanical energy. But if you let it be, and just let it activate some device without applying any external forces, then this will be the same. In this case, that's what's happening because it's coming down a frictionless ramp. There's no strings or anything attached to it, so there's no externally applied forces. So that means that this is the same all the time. All right, so let me write that down for this problem. The kinetic energy plus the potential energy changes zero, never changes. And let me write this as Tx minus Ti plus. Now, for this potential energy, if you have more than one type of potential energy in your problem, you've got to include those. In this case, there's two different types. There's both gravity acting and there's also a spring. Let me write those both in here. So I'll put U spring, I'll put its final, minus U spring initial, and then plus U gravity final, minus U gravity initial. Okay, this seems tedious, but I would do this every single time. In fact, I personally do this every single time when I make problems and I write the solutions. Even when I'm doing it on my own just to get the answer to plug into TED, I still do this. Because it's impossible to make a mistake if you do this systematically. It also takes care of all the signs. And we'll talk about the signs as far as gravity in a second. But the signs here, there's no question about whether it's negative potential or negative gravity potential, things like that, which can be confusing. Okay, now that you have this formula, we want to plug in what we know. It starts at rest and it ends at rest. So which two terms here are zero because of that? Kinetic energy terms. There's no velocity at the ends of the beginning. So these are both zero. And then also, you want to find out when the gravitational force is zero. So first thing you got to do for gravity is always pick a zero point. And that's up to you. You can pick it, I'll pick it either where it starts or where it ends. Because it makes things easier. It makes one of the terms drop out. Let me pick the 0 point where it ends. I like to pick it at the bottom. So I'll pick this as my u equals 0. And draw this under picture every single time. I would be really particular about drawing on the picture because then when you go back and look at it, it's very obvious what's positive and negative. So this is my u gravity equals 0. If that's my 0 point, then it starts at positive potential energy. So my u gravity final is 0 because I set the final point equal to 0. That was my choice. It won't change the answer depending where you set it. All that matters is the change. And then for gravity initial, well, the gravity initial is starting above, right? So I need to find out mgh in this case, which means I need to find out the total height that it rose, that it fell, right? So I need to know what this h is. Because it's not how long it went down that way, it's only what the height is off the ground vertically for the potential function. In this case, it's mgh, but I'm not given h, I'm given d. And I'm also given that this angle is 35 degrees. So you can use simple trigonometry to find out what h is. H is, let's see, so sine theta is opposite over adjacent. So h is d sine theta. So that's this portion right here. And then lastly, I need to figure out the spring energies. Spring potential energies are always positive because there's a, let me write out the spring potential energy here in case you don't know. So no matter how you stretch it, if you stretch it backwards, your x is negative, but you're going to square it, so it'll become positive. So this is what we'll call it. So don't have to worry about the signs there. But one of these is negative. When you start out, the spring is uncompressed, so the initial spring energy is 0 before you let the block go. And then when it gets there, when the spring is totally compressed, it wants you to find the delta x there. So I'm just going to write this as 1/2 k delta x squared. You can put x whenever you like. So everything else dropped out except for that last term, which is hd sine theta. And in this problem, I'm leaving everything as a variable, which is good practice. This we know, this we know. Sorry, why did I write hd? I meant to write d. mg sine theta. Minus mg d sine theta. All right, so here we know the theta, we know how far I've traveled on the ramp, we know these things. I think the spring constant is given, is that right? Yeah. You know things, you can solve for delta x, you see things in terms of algebra.
What are you going to line up the initial spring potential energy delta?
Yeah, because when you have this thing on this ramp, the spring is just sitting there, nothing's pushing it or pulling it, so it's not compressed. So if it's not compressed or stretched, it has 0 potential energy. I can't do work unless you stretch it.
You choose 0 point compress.
That's for gravity.
Okay.
Yeah, for spring, you just have to look, think about the spring. Is there anything resting on it? No. He brings up a good point, actually. For springs, you only just set a 0 point. For a spring, a 0 point, the 0 point is when it's uncompressed. That's your 0. When it's compressed, then that's how much it changes, so that's your delta x. Or if you stretch it out, that's how much it changes. Your 0 point, naturally, it makes sense to just make it your, where it's uncompressed. Yeah.
So when you're plugging in the values into the equation, for K, would we put 30,000 kilonewtons?
Yeah. Any other questions?
If we prove the spring, whereas the potential energy of the spring to be positive?
It's always possible. Yes. Because no matter how you spread it out, your x is squared.
Can you tell me why you substituted mg for mgg?
Oh, yeah. The potential energy of gravity is mgh, and then h is the vertical distance we're looking for. But we're given d, so I used trig to find h trigonometry to find out what h was in terms of d. Any other questions?
So that change, delta x squared, is just, it'll just be one single number. You can take the square root of it.
Yeah. Yeah, sorry, you can write x and delta x wherever you want. Yeah.
When I solved this problem, I didn't use I didn't have the potential spring, potential gravity, so I'm not sure how. Looking at how I ended up, I ended up with the same thing, but was that using a completely bad logic, or
What did you use instead?
I just had I had potential for, initially it has the potential of gravity, and finally it has the potential of the spring. Yes, so, but you have four terms for potential in your initial equation before you cancel. I just wanna.
Yeah, well, you just did this in your head.
Would I, but I didn't think about that. Would I have a similar scenario, like if they both had initial kinetic energy, would I lay out like, like a full 8 terms or something for it?
Well, here, springs don't really have kinetic energy. We don't talk about springs moving.
Right.
The only thing that a spring would have is potential energy. So you only have 2 terms for kinetic.
Okay.
Are there any other questions?
Can you solve the problem using forces instead of using energy? I feel like that's what I saw.
Okay, so the question is this: can you solve a problem using forces? Yeah, you could. And here's how you would do it. And I want to explain why the energy situation. We teach you energy second because it's easier. Every time you learn something in any class, you learn the easier way backwards. So you use the easier method before you learn something. The reason you don't use forces here is because if you use forces, you could use forces. You could draw a free body diagram, find the forces, okay? That would give you the acceleration now. And then you could find out using the acceleration what the final velocity is here. And then you can figure out what the force therefore is upon the spring, and then figure out how far it stretches based on those forces. It would be like a 3-step problem. It would take, I think, a 30. Any other questions?
For the problem you're just trying to solve for
Shoot up. Let me move on to a different problem. Let me try. Let's go with the numbers. Let me do one from the book, actually. This is number 106 from the book, chapter 8, problem 106. I think this is a nice problem. Now, this one I suggested for a book problem, so the solution is already posted online.
Is there like for the delta U change in potential energy, when you're dealing with springs, you do it for like, you use the delta U for the spring and the delta U for the gravity? Unless it's just horizontal, right? It's just...
Yeah, if it's horizontal, you don't need to worry about gravity.
I just want to know how you determine that changing kinetic energy and potential energy equals 0 instead of like the work applied minus the work dissipated.
It does equal the work applied and the work of friction, but there's none in this problem. So I just didn't write them there.
Oh.
It does equal that for this zero in this problem. Okay, so number 106 says this. It says, the spring in the muzzle of a child's spring gun has a spring constant of 700 newtons per meter. To shoot a ball from the gun, first the spring is compressed, and then the ball is placed inside the spring, inside the gun. The gun's trigger then releases the spring, which pushes the ball through the muzzle. So this thing is shot out. It's like a spring gun, if you see it. And then the ball leaves the spring just as it leaves the outer end of the muzzle. Okay? Now, when the gun is inclined upward by 30 degrees, a 57-gram ball is shot to a maximum height of 1.83 meters. So what this is saying is that you compress the spring, and then it shoots it off, and then it goes up, and at its top right there, this distance here is 57 meters. It's 1.83 meters, sorry. That's how high it gets, and it starts to go down. This is like a projectile motion problem. And then you have to assume that the friction is 0 in this case. So the question is, at what speed does a spring launch the ball? Which is called, what's the initial speed? When we talk about projectile motion, it's asking you what's the initial speed. So let me draw this problem up here. Again, chapter 8, 106. This is like a little spring-loaded gun, and it shoots this ball up. And at its highest point, it reaches 1.83 meters. And this degree is 30 degrees of centimeter. And the spring constant is also given to you. It's 700 newtons per meter. And then lastly, it gives you the mass. I just write these numbers up here so we know what we have, even though I'm looking until the end. And the question is, what is the initial velocity? Initial speed, what's the initial speed? So remember, keep in mind that this thing is going to be shot, it's going to be shot at an angle, so it's in both an x and y components. And we need to find the initial speed. Now we've done this before we've done parts of this kind of fun using kinematics at the very beginning of the class. But this is different because now it's added an extra dimension to the problem. It's giving you a spring. Right? So the spring is going to shoot this ball up, and you want to find out what the velocity is. What's nice about this problem is that there's no friction added. There's no friction or applied forces. So at all points in this entire situation, the energy will be the same because it's conserved. When I write this formula now, which I'll always start with, if I consider my whole system as this whole gun and then the ball afterwards, so this whole thing is my system, there's no extra added work I'm doing to the system because I'm not pulling and pushing the system. And there's also no area system, so these two terms are zero. That means that the kinetic plus the potential energy at all given times is going to be the same. So what I can do is I can figure out what the missing quantities are by using my knowledge of what the energy is at one state of the system. If I know what the energy is now, I can find out what it is later. And if I know that it changes form, I can find out missing quantities in that form. All right, so what I'm going to do is write down, let's write down Tf minus Ti. So these are the initial and final kinetic energies. Is going to be the total of the potential energies. And in this case, there's two types. Again, there's a gravity and there's a spring. So I'm going to write terms for both of them. So I want to find the change in the spring energy. And I also want to find the change in the gravitational potential energy. Okay, any questions on the first step? Yeah.
So you said you chose your system to be the whole thing, so that it's equal to zero?
Yeah, so that's a good question. The reason I'm choosing a system, what that means is I'm choosing what I'm going to call inside, everything inside of here is my system. If this is my whole system, I need to ask myself, is any work being done on a system that's not within it? And none, so that makes the right-hand side zero. If I chose a system as like maybe just the spring, just the ball, without the spring, I'd have to consider the spring as an applied force, and I have to find out what that is. But that wouldn't make sense because it's actually a potential force, so I want to keep that. It's a conservative force, so I want to keep that over here. So consider the charges. This is something many of you guys already do, just kind of naturally, just kind of subconsciously you already do this. I guess it's good to be explicit about it. Okay, any other questions on that part? Yeah.
So the spring is not applied force, or it is?
It's a conservative force, so it's going to be under potential forces. And it's conservative. It's not an applied force that's not conservative. You can put it over here, but it's a lot easier to use potential function.
But if you chose your system to be just that gun, would anything outside of it be the work applied, which would mean like the gravity on the outside of it, like when it's projectile, wouldn't that be applied then? If you chose your system just to be the gun?
Let me say it this way. Let me say that, I guess I should be a little more precise. This applied force is anything non-conservative.
No. Okay.
So non-potential force. Gravity and springs don't fall in that category. So there's a way to do it that way, but it just takes a while. You got to do it. Yeah.
And because of that, because the spring inside the gun is compressed, so that means it has potential energy.
Yeah. At the beginning, it has spring potential energy. So let's go through this and find out what all the zeros are in this formula. All right? The question is asking what is the velocity right when it's released? Okay? Right when it comes out of the gun. So there's a couple things I can do here. You basically want to choose different points to find out what you're going to use for initial and final. And the reason I'm saying that is because there's a couple of choices in this problem. Let me do it one way and see if that works out. So what I'm going to do is I'm going to consider the point where I first cock the gun, right before I release it as the initial point. And then the final point will be right as the spring unloads and this ball is right about to leave. Okay? So if the initial point is right when I have this thing cocked, in that case, the kinetic energy initial is 0. The spring initial is non-zero, but the spring final is. So the spring initial is non-zero. The inertial gravity is also 0. Okay, and then after it releases the spring uncompresses and releases the ball at that moment, there's going to be some kinetic energy because it's going to be flying through the air. There's not going to be more spring energy because now it's uncompressed. And the gravitational, they kind of assume that this gun is small, so let's say there's no more gravitational. Still, we don't move this much. Just ignore that one. Anyway, I'll tell you how long we've done it. So we'll just keep it like that. And so what's missing here is the final kinetic energy, which has the quantity I'm looking for. So that's probably good to have the problem. And I also have the spring energy at the initial point when I caught it. So let me write down these two terms. Give me 1/2 m v squared minus the spring energy initial, which is 1/2 kx squared, or delta x squared, either one, equals 0. Okay, let's look at here to see if we have everything we need. We have the mass, we have k, we do not have x. We don't have x, so we can't solve this using this method. Right? Because I don't know how much it's compressed. In fact, that's the second part of this problem. Find out without this. Yeah.
Why is there no initial?
Did you just like holding it there right before it launches?
Why did we end up getting rid of the spring final?
Because once this thing is uncompressed,
Okay.
yeah, it's like. Okay, so again, the point here is that I have the velocity. I'm looking for velocity, but I don't have this x, so I can't actually find out what the velocity is. So this is no good. So we can actually do something else because there's something else. We also have the energy here. Let's try that. We know they gave us a little bit more information. It tells you it reaches as high. So I can maybe use that point as my final, and the point where it lets go of the gun is my initial. Okay, so instead, so I'm going to choose the initial point as when the ball first comes out of the gun, and the final point is when it's at the very top. Let's see if that works. So I'm going to have the same equation here, but different things are going to be 0. Okay. Now, when it's first let go, of course, there's going to be some kinetic energy. So I got to keep the initial kinetic here. The spring is no longer part of the problem because I'm talking about when the spring has already been released. So there's no more spring energy either at the beginning or the end. So these don't matter here. The initial gravitational potential energy is 0, for that 0 point down there. That makes sense if I hit the ground. Okay, and I also know my final gravitational potential energy. It tells you how high it rises. So I have mgh for that part. Those three terms drop out. My initial kinetic energy is 1/2 mv naught. So my final kinetic energy is 1/2 mvx squared. And my initial is 1/2 mv naught squared. Okay? But I'm in a similar dilemma here. I don't really know. I know all this stuff, but I don't know what the final velocity is, or do I?
Is it 0?
Yeah.
I'm not good.
Okay, let me get this question answered first. It's not 0. The velocity at the top, can you tell me the speed at the top is 0?
Oh,
It's not moving with the very top?
yeah, it's moving it horizontal.
What's 0 at the top?
Vertical velocity.
The y component is 0, but the x component is not 0. However, I do know what the x component is relative to the x component when it was launched. What do we know about the velocity in the x direction? Constant. It's constant because there's no acceleration. So the final velocity, let me write this out in terms of components. I'm going to have 1/2. And so the final, I'm going to call it v final in the x direction, and then v final in the y direction. Those both matter because they're moving in 2 different dimensions. And then same for this guy. And as we discovered, the final in the y direction is 0, so I don't even worry about that. Okay? But I still have 1, 2, 3 variables here. Oh wait, this is the same. So also we know that the x direction, the velocities are the same. So I'm just going to call them Vx for both of them. Because it doesn't change. So I still have one more variable. I mean, I have Vx I don't know, and I have V naught y I don't know. So we have to kind of find something that relates these. And we can use the fact that it comes off at 30 whatever degrees. 30 degrees. So if we use that, let's actually write these components in terms of the initial velocity. So I talked about at the beginning, the velocity is like this. The V naught x is in that direction, and the V naught y is in that direction. And if I know this is 30, I can write both these components in terms of this velocity and that angle as well. Let me go ahead and do that. So the x component is simple, it's just cosine. This is V cosine theta. And if I plug that in here, I'm going to have, so the Vx is going to be V cosine squared theta. That's for the x component. And then for the y, for the initial, you're going to have, the Vx is the same, so again, it's V cosine theta. And then the y component is going to be V sine squared theta. And now I have it in terms of things I know and what I'm looking for. I have m, g, and h are all given, theta is given, but v is not, so I can in theory solve for v by plugging this in. So let me run through how we did that problem one more time before I answer questions. So again, the question was asking what is the initial velocity? And we wanted to find out what the velocity is by giving knowledge of what the energy is at different points. So I tried using the equation with my initial point as when the spring was compressed, and then the final point is when it just launched. That didn't work because I didn't know this number, so I can't find out what the total energy was at the beginning. So I can't use that formula. So instead, what I'm going to use is I'm going to use my initial point as when it first fires, and use my final point as when it's at the top. And if I do that, then I get this formula, and it turns out I can write these velocities in different components in terms of the initial velocity. And now I have it in terms of what I'm looking for and everything else I know.
I think you're missing a square on the.
You still have a question?
I was just gonna say, are we ignoring the spring height when we're accounting for the potential energy, the max height?
Yeah, when there's nothing resting on the spring, its energy is 0. Oh, you're saying, yeah, we're not, yeah. Yeah, I say it's very small, it's not really.
How do we solve the cosine squared?
You plug in theta and just square it.
So how can we assume that the gravity's oh wait. Did we just describe did we decide the gravity was negligible?
No, it's
No,
here.
okay,
It's right here.
okay. Yeah.
Any other questions? So it may take a couple times, but there's enough information in the problem to solve it. You may have to use different points of reference to solve it. Yeah.
Sorry, can you just give the last two lines
Yeah, I don't want to rewrite them. Let me just rewrite this one. So this just says Vx squared plus Vy squared. Vx squared plus V naught y squared. And then down here I plugged in, this is V, sorry. So this is V squared times cosine squared theta, V squared cosine squared theta, V squared sine squared theta.
Does that sine square theta have to be initial, like V
Yeah,
naught?
this is all the initial.
All initial.
Any other questions? I kind of added a step here I didn't need to do. I mean, this whole thing is just V squared, so I don't need to break it up like that. But It's not long. Let me do it on the homework assignment. Let me, go ahead and answer, number 5. This is the one where you have like this crate that's being suspended by a rope and you push it to the right, and then you hold it there. And it asks a couple of questions based on that problem. The first question says, read this out actually. Look on page 163 of the